Jaco on LLM Magnon Scattering.
Excellent, thank you, Kostas. Let me just also start by thanking the organizers for what's been a wonderful work so far, and I'm really looking forward to the rest of it, and of course for the opportunity to present my work. I should start with the footnote that this is still very much a work in progress, so that although this is the title, this is certainly not a solved problem yet. However, I wanted to share this with the audience because recently, I think, with some appropriate massaging of the equations of motion, it really takes a surprisingly simple form that I think there might be an elegant solution for. And if anyone has some very good suggestions, please come afterwards and we can chat about it. So for those of you who have been to some of my previous talks will know this LLM setting quite well. So the first part of the talk is certainly going to have quite a bit of overlap of that, but I'll try to go through this briefly. And then the second half will be a particular application that I've been busy with the last while on this. Okay, so I'm going to start with some motivation and background. I'm going to define exactly what these Magnon excitations are, both in the gauge and the string theory context, and then move to this particular application, which is the LLM Magnon Scattering that I'm interested in. For those of you who want to just have a look at the setting for the problem, and that I've already alluded to, here are some works that we've studied this particular LLM setting. I'll describe exactly which subset of this we're interested in, but this is all work related to that that's probing a particular conjecture that was made in this 2016 paper that I'll get into shortly. All right. But just a broader overview before we go into the specific setting of the problem. The setting is ADS-CFT. So that's this famous conjecture between Tartubi string theory on ADS5 plus S5 and NS for superanimal gauge theory, where there should be a one-to-one mapping between the gauge invariant operators in the states. The quantum numbers of these things should match, and in particular the energies of your string state should match with the dimensions of the operators on both sides of the correspondence. Specifically in this classical treatment of string theory that I'm going to get into later, we're going to compute these energies explicitly and see that they do match up, and that's how you identify the correct states, the operators that you're interested in. And of course, there's no explicit proof of it available, but it's past a multitude of highly non-trivial checks. And one of the areas that has been particularly productive is in planar ADS-CFT, where these integrable structures have been identified, and this has allowed the computation of anomalous dimensions to extremely high accuracy through the quantum spectral curve. Recently, there's also been developments in computing the three-point functions using these tools of integrability that's really powerful and has allowed a whole set of tools into these computations that are really quite powerful. It's on this point that I just want to point out where we're going to be different, because I'm going to be discussing something that's not in the planar limit of ADS-CFT. But there are many different ways that one could consider a non-planar limit. For example, studying finite incorrections. So there's one possibility. The limit we're going to be interested in is where we're still at large N, but the operators we're interested in, the correlation functions, you no longer get a good answer if I just sum the planar diagrams. And the reason for that is quite simple. This approximation, this topological expansion, works well if the operators inside your correlation function scale like square root of n, as I tend to infinity. The operators we're going to be interested in are going to scale either with order n or order n squared. And what you find in that case is that you can no longer sum just the planar diagrams to get a good answer. You need to sum all the diagrams. But there's a set of tools, these Schur polynomial technology that's been developed to do that. I'm not going to go into that in too much detail. My focus is going to shift to the string theory side quickly. But just know that there is a set of tools that you can use to compute these anomalous dimensions of operators, etc. All right. So I'm going to start with the string theory side of the correspondence and just give a short motivation of where this comes from the gauge theory side. So the setting that we're interested in are these LLM geometries. So they were written down by Lindgren and Mandelstam from their name. This is the form of the metric that you get, and you can think of this as resulting from, so as I said, if you're doing ADS-CFT, you typically just have the ADS5 plus S5 metric. What you've done here is you've taken a very large collection of Rapley 3 balloons, put them on the ADS5 plus S5 background, and they backreact. They're massive objects. You have to take the backreaction into account, And this is the metric that results from some configuration of these active three branes. Now, the whole form of the metric is not going to be important for later on. I'll give you a much simpler version of this in the later slides. The only thing to take away from this is that this metric, even though there's a lot of functions appearing in it, there's only one independent thing that you tune, and that's this function z. If you have this function z, everything else, g, h, v, is determined in terms of this function z that you have. And z itself is sourced by a Laplace equation. So if I give you a boundary condition, an appropriate boundary condition for this Laplace equation, that's going to fix the function z uniquely, and that is going to fix all the other functions in this metric uniquely. So in other words, to each boundary condition, there's a corresponding metric. You require that these are regular geometries, and that turns out to give the condition that if I go to y is equal to 0, so what happens then is that these two three spheres tend to shrink. You compensate that by having only one of the three spheres shrink, so in order to maintain a regular geometry, and you can do that if z goes to plus or minus a half. Then one of the three spheres doesn't shrink to 0 as I approach y is equal to 0, and this is the boundary condition. You're going to get a coloring of the LLM plane. So an example is one that I've written on the right-hand side over there. So this is on the LLM plane. Whenever you see black, that z is equal to minus a half. Whenever you see white, that z is equal to plus a half. And yeah, so this is a typical boundary condition that you can get for LLM geometry. And what's really nice about them is that they have this very simple map between these geometries of the circular type and these LLM on these Young diagrams. And the way the mapping works is that, well, this is the Young diagram due to this geometry that you have over there. And the way you should have is that there are n rows in total. There's a number of n1 that's missing. That maps into the area of the center black ring. Then I have a number of n1 columns. That maps to the white area that you have in between. And then I have n2, that's the area of the outside ring that I have over there. So for example, if n1 was to shrink to 0, then this white region shrinks to 0. You just get a black disk on the LLM plane, and that is ADS5 cos S5 geometry. The LLM geometry corresponding to that boundary condition is just ADS5 cos S5. So what you've done now is that you've you have these, and you can think of these white rings over here as being a bunch of these three branes that I've basically put in between these black disks that I have over there. And this, as I said, this will give me some LLM geometry that you can determine. And this is the Young diagram used to label it. It goes further than that, though, in the sense that the Young diagram here is actually labeling a shear polynomial. So a shear polynomial, think of this as a shear polynomial labeled by this Young diagram from Z fields, for example. That combination of the three branes, because that's what these objects are due to, that's some bound state of a large number in one the three branes with a certain angular momentum. That is the geometry that they give after backreacting on ADS5 cos S5. But for our purposes later, we're just going to be studying classical string theory, so we're just going to be using the metric, but it's useful to keep in mind where these come from. Now, we got interested, I think that's actually just one more slide. So just, there's been something said about these shear polynomials up to now, but it's useful just to give a few brief points on it for those of you that aren't too familiar with it. The first is that all it is a different basis choice for operators, for gauge invariant operators. So one of the bases that you might know really well is the single trace basis. There's a way to take any single trace operator and map that into some combination of shear polynomials. So you have got a combination of three shear polynomials on the right hand side, and this is the same operator as the one on the left hand side. So it's just a change of basis, but it's an incredibly useful change of basis. Because what happens is that these single trace operators are orthogonal in the leading order in 1 over n, as long as the operators I'm considering here only grow as or the square root n. The moment that they go beyond that, then you get non-trivial mixing happening between these operators, and it's no longer an orthogonal basis, a good basis to use. The shear polynomials, on the other hand, they're orthogonal for any value of n. So that's why they're a particularly useful basis. And this mapping between these Young diagrams and these LLM geometries And I've explained previously, that's another reason that they're incredibly useful in our context. I should just maybe mention, just to point this out in this mapping, notice that the vertical sides that you have of your diagram map to black rings, and the horizontal ones map to white rings. And here I've just chosen an example with 3 rings, but you can have an arbitrary number of rings. Think of the ones later as having all the one number of rings, but this is the setting that we're interested in. So, as I said, I'll only go into the gauge theory side briefly, but it's really useful because this is where the conjecture is formulated most efficiently. So, what we asked in this paper from 2016 was, can I get a notion of localized operators in these backgrounds? So, say for example, I give you a background, so this should really be the shear polynomial with this background, so that's some configuration of these that I have. And now I have some excitation, so some operator consisting of Z and Y fields, and I want to attach it to the top right-hand corner of this. What is the operator that conveys both that for me? I have some background and some excitation that I've added somewhere in the background. Well, the operator that conveys this is the following. So here is this shear polynomial, restricted shear polynomial built from Z fields and Y fields. All you need to do in order to localize this excitation at the top right-hand corner is glue these Young diagrams together. So these Young diagrams are over here. This is a Young diagram that organizes the Z and Y fields, both of them. This one organizes the Z fields, that one organizes the Y fields. To get the combined operator with background and excitation, I need to take everywhere where Z is appearing, there's a Z in the excitation and in the background, I need to enlarge those Young diagrams by gluing them together. All the ones that don't feature in the background, so the Y fields, they still form there. They don't change at all. It's only these 2 diagrams that are enlarged. But this is the claim that this is the operator due to adding an excitation to the top right-hand corner. And just another footnote, I've drawn it here for a 5x4 Young diagram, but we have much larger ones in mind. So it'll be typically an operator that has in squared boxes, a large number of rows and columns, and the excitations will typically be ones of order square root n. And I want to attach to these corners.
So your background will be made of Z's?
Yes,
your V is
exactly.
made of Z's, and then you add in a small amount of Y's.
Precisely, precisely. And that's exactly where the magnons are going to come from. These Y's will be the impurities that give you the magnon excitation. So what we then did in this 2016 paper was study these kinds of operators where, well, you can take an operator with Z's and Y's. I know exactly what the operator is. The one-loop dilatation operator is known exactly from this work by Bison. So write down this operator and let the dilatation operator loose on this combination that you have. What you find is, well, quite natural to understand. So you've got a derivative with respect to the Z and a derivative with respect to Y for the dilatation operator in the SU2 sector. But this does not discriminate at all. If it sees a Z field, it will certainly act on it. So it sees the Z fields in the background and the ones in the excitation. The Y fields only appear in excitation, so the derivative has to act there. But the derivative otherwise can act on any one of the Z fields, either ones in the background or the ones in the excitation. So you get 2 kinds of terms. Terms that where this Z only acts on the Z field in the trace and places a Z and a Y field back at the same corner where I've attached the excitation. And then you get a bunch of terms that mix these background fields with the trace. So either taking a field from the background into my excitation, or taking a field from the excitation into the background. All these terms appear, but you can write them all down, and what you find is that it's terms of the second type scale like 1 over n, as long as these corners are well separated. So provided that where I've added the excitation, all other possible locations where I can add or remove a box is well separated from it, these terms are suppressed by a factor of 1 over n. So you only get terms of the first type. So, and this is where this notion of localizability of this excitation comes from. It's never going to move away from this corner to which it is attached. In fact, what we noticed back then also further is that the only difference that you find when I compute the anomalous dimensions, and this was done explicitly at one loop, is that there's an effective rescaling of the coupling, where you take your Doof coupling and you just rescale it with this order 1 number. N is just the usual N that you have. N effective is the weight of the corner box to which I have attached this excitation. But that is the only difference that we observed in this. So we made a conjecture that in In fact, when you attach any operator to any loop order, this is the only difference that you should see. And when I compute the anomalous dimensions, there should be this order 1 rescaling of the 12th coupling. There was a paper last year in June by Robert and collaborators that stated this conjecture quite explicitly and very clearly. Basically what happens is that when I attach these excitations to a corner, they're localized at this corner. I only see other boxes that I end up attaching to the corner and nothing else. This gives rise to an emergent gauge theory, ineffective gauge theory. And if I study the planar limit of this emergent gauge theory, then the conjecture is that this should be isomorphic to planar n is equal to 4. These two have they're essentially the same, only with this change in n that you have. And I checked this with 3 different computations. The first was just showing an isomorphism between the operators. So for every operator in planar n is equal to 4, you can write down a corresponding localized operator at a particular corner. The scaling dimensions of these operators match, and the 3-point functions match. And since this is a CFT, this implies that they must be equivalent, because this is all the information needed to find all the correlation functions. Oh, sorry about that. I should also point out work by David Bernstein and Alexander Miller have reached similar conclusions in the language of code subspaces. That's along, as I said, similar conclusions to this, that excitations are localized at these corners. But the point is that this is a conjecture with very clear predictions to test now. Because the only difference you should see is this rescaling in n. So in other words, take your favorite gauge theory operator for which you can compute the anomalous dimensions, write down the corresponding localized operator, and compute it. And the only difference should be that rescaling in n. At the same time, take your favorite classical string theory configuration on an element background, write down the corresponding classical string, take your favorite string solution on ADS5 plus S5, and now find the corresponding string solution on your LLM background, and check that the energies also show this rescaling in the dispersion relation. And this is a game that we've been playing for a while. I can just point some of this out perhaps that will be relevant for this talk. So a class of excitations that's really useful are these Magnon excitations. And what they are is, think of order 1 impurities that I've added to a sea of Z fields, or the square root in Z fields. And the location of each of these impurities has an associated phase that's going to be related to the momentum of these Magnons. So the Y is, for example, P1, X is P2, Y is P3, and this Li is the position that they are in. So whenever they move around, there's some associated phase with that. What's really nice about these is that there's this residual issue2 squared. So each of these impurities transform on the centrally extended issue2 squared. And you can use just the closure of the algebra, the symmetries of this, to argue for this exact dispersion relation. So for each of these impurities, this is the anomalous dimensions valid at any value of lambda that you should find. And as I said, this is if they're attached to a single corner. There you see the R0 scale as predicted. But you can also consider something more exotic, where these impurities are stretching between different corners, not ones that just have a rescaling of R0, but between ones that have R1 and R2. This is the generalized dispersion relation that you can find. I'll show you later that the string solutions, the classical string solutions, really do show this this form over here, strong coupling. And I should also point out that the 2 Magnon S matrix of these impurities can also be determined up to the overall phase. So this is the kinematic part of the S matrix, and this can be computed with exactly the same symmetry argument. When we're going to be studying the scattering solutions, what we're after is a check for this overall phase of the S matrix. So from the scattering solutions, you should be able to read this off, and this should also match with the prediction. So some of the checks that has already been done here, I've alluded to the one loop dilatation operator. That's an explicit computation. There's a check at the 2 loops. So you basically write down what the 2 loop dilatation operator is, and check that it matches with this what the kinematic part of the S matrix should be. The kinematic factor of the S matrix I get out, does this match with the 2 loop dilatation operator? On the string side, we've computed Magnon solutions, the dionic giant Magnons and their finite size effects, showed that the dispersion relations match exactly. And this is significant because when I say match exactly, I mean up to this rescaling of the edge at which it is. And this is significant because this is a check of this overall phase through the so-called Lucia corrections. What the scattering solution would give you, though, is really an explicit form for that overall scattering phase. And we've also done SL2 string computations. And just checked that the dispersion relation does this.
So when you say finite size, in which operator is finite size?
The excitation.
The excitation finite size.
The excitation is finite size. Yeah, so exactly. So your LLM background is still, that's still the classical same geometry that receives no corrections. It's the excitation that you add that's going to receive finite size corrections, and that's what you compute in this one over here. But yeah, and as I said, that matches exactly up to this overall scaling that you get. So just as a introduction to what I want to get into in the scattering section, let me just study these Magnon solutions that you get explicitly. Let's just start with the point-like strings, and this will just point out some of the novelties that you get in these LLM backgrounds when I study the classical string theory. So as promised, I've just simplified things over here. So before I had a 10-dimensional LLM geometry, a metric, and now I'm just going to simplify to a 3-dimensional one, and I'm also going to go onto the LLM plane. Send y is equal to 0. This is how the metric I'm left with. Just written out explicitly. Now I've only got this function v and h appearing, and in fact, if I'm on the LLM plane, then these take a very simple form. So you'll remember that these boundary conditions I wrote down with these concentric rings. The input for v phi is the radii of these concentric rings. So when I'm summing over all these rings that you get. Wherever I have a ring edge, I produce a pole in v phi. And then the v phi is just going to depend on which ring I'm sitting. That's going to fix whether it's r squared or ri squared, and it's also going to fix a sign. Whenever you have a black ring or a white ring, this is going to affect the sign. That's not too important for now. The most important feature of this is that whenever you reach a ring edge, you pick up a pole in v phi. And here I've also written this function h to the -2. This is given entirely in terms of v phi. Just take a derivative with respect to r of v phi, and this is what it is. So this whole metric is going to be determined entirely in terms of this function v phi, which in turn is entirely determined by your poles. The poles and the radii of the rings, the poles that I have on the LLM plane.
Sure. Your rings used to have a width. Do these also have a, or are you thinking of the width of the ring as a sum over different radii?
Oh, so maybe I should maybe I should just draw a picture there just to make this exactly clear. So let's say that I have this, the one that I had previously, where you just have this center element there, and then I'll have a white ring, and then I have another black ring around that. So in this case, v phi will be 3 terms, one for each of these rings that I have over here. Here I'll have R1, say, R2, and R3. And so the terms that are going to be present in v phi are all going to have a factor like something over r squared minus r1 squared. That's the radius of the center one. Then there will be another term, that's r squared minus r2 squared. And another term that's going to be this over r squared minus r3 squared. And that form I've written down there is just, if I'm sitting in the center over here, then v phi is going to take the form, it's going to be from that second term. So everything is going to have r squared at the top, and then you're just going to have alternating signs. I think this will be the form for that. Whereas if I'm in the outer ring, then this will be replaced by r1 squared, r2 squared, and there's still a radius outside of it. But these specifics are not too important for form. Now, the most important feature in the solutions I'm going to show you now is the pole structure. The fact that whenever I have a ring edge, I pick up a pole in v phi.
And the pole is when you switch boundary condition.
Precisely.
Okay.
Precisely. All right, so are there any more questions? So one of the first kind of string solutions that you can try to write down are point-like strings. So I'm just going to set r to be equal to some constant radius. I'm just going to let phi rotate at minus t, so at the speed of light. You can check that it solves the equations of motion quite trivially. And you can compute E and J, conserve charges, and show that they're equal to 0. And this matches the intuition quite nicely. I imagine these point-like strings are due to operators built just from Z's. If I attach Z's to my LLM background that's built from Z fields, I'd expect that they should be pinned to the geodesics. And they should be half BPS. That's why I should expect this relation. So, as I said, there's no difference between the ADS5 plus S5 solutions and the LLM background solutions, only until you start to ask, but for which values of R0 is this an allowed solution? For which values of R0 do I see conformal gauge and wall sheet? And the values where this is are all the ones where your function h minus 2 vanishes. So just a reminder, this is the function h minus 2. This needs to vanish. I've got something that goes like 1 over 3 phi. So this is going to vanish wherever there is a pole in that function v phi. So, so as I said, whenever R0 represents a pole in v phi, that doesn't allow the radius for this point-like string. And this is what's quite novel about these LLM geometries. For ADS5 plus S5, the boundary condition was just a single black circle. So there was a single geodesic. There's a single location where I can add Z fields, and they rotate along the geodesic. In these LLM backgrounds, you have multiple choices for these geodesics. And this is exactly what we should expect from these operators dual to them. They dual to these LLM geometries. Each corner of the Young diagram is one where I could potentially add or subtract these Z fields. And these should be represented as geodesics in the LLM plane and a possible location for my point-like string to rotate. So this is what you do see. And it's these boundary conditions in these solutions that's going to be quite key in classifying them. And that's why I said the pole structure in B5 is really an important thing. So just to go on to these Magnon solutions, they also satisfy things quite simply, in the sense that we know the giant Magnon solutions from Hoffman and Mandelstam for ADS5 plus S5. If you plug in the same ansatz for the giant Magnon solution, so what this is, it's a solution that retains its shape, and its endpoints are also still in geodesic. I imagine that this is where the Z fields are located, and they rotate at the speed of light along the geodesic. And the solution itself retains its shape. And you plug in this ansatz, this solves the equations of motion. You can compute the conserved charges again, E and J. I should mention here that when I chose this subspace, I had in mind that the excitations I'm going to be studying are ones that are only specified by energy and the J, so built up from Z fields, and then possibly some profile field that can be associated with the other numbers that's specified. And what you find here is that this is the dispersion relation. Here I've written it where I've got an excitation stretching between two different geodesics. That's an allowed solution. This is the dispersion relation that you write down, and this matches exactly with the large coupling exact dispersion relation I showed you previously. So that's why we know that this is the right solution to associate with those excitations. And what you find is that inside the dispersion relation there is this angle delta phi. This is the angular extent of these giant magnons. I'll draw you a picture in a slide of this now. But they're essentially represented by straight lines on the LLM plane, stretching between two geodesics. And in order to recover the same dispersion relation, I need to identify this angular extent with the momentum of these magnons I have. All right, so these are just some of the classical string solutions that you get. As I say, they're identical to the ones you write in ADS5 plus S5. The other solution where this is true is for the SL2 string, where the solution is. But any of the other solutions, the ionic giant magnon, the finite size forms of these aren't just simply the same ansatz that you plug in. There is a V phi dependence that's entering into your solutions in all cases. For the scattering solution, this is most certainly also the case. So the solution that's known for ADS5 plus S5 is this one of Skretler-Volovich. This is a particular form of it. So here I've got two magnons, one with momentum P1, the other one with momentum P2. The solution is written in terms of these three functions that I have here, t, r, and I. So there I've written t. Notice that I will switch between p1 and these ta, tb numbers, but they're just numbers that are labeling the solutions. And here I've got phi and I've got r. And it's useful to maybe just plot them for what you have. So here I have that configuration that I told you. These magnons are straight lines. So here I have a configuration at t is equal to minus infinity, for example. In this example, I've chosen p1 to be, I think, pi over 4, and the other one to be 2 pi over 3, the longer one. And so this is the solution that you get at t is equal to minus infinity. And now I start waiting. And I wait for an incredibly long time until I reach t is equal to minus 10. It's still looking like this. T is equal to minus 8. Start seeing a little bit of a difference. T is equal to minus 6, minus 4, minus 2, 0, 2, 4, 6, 8, and 10. So there are a couple of features that's important here. You see that it starts off as two distinct magnons, and it ends up as two distinct magnons, but only the momenta have swapped. So the short one was sitting at the top, and now it's sitting at the bottom. So this is an elastic scattering process that's taking place. And this happens extremely quickly. It's only for a really small period of time that anything happens in the solution. As I say, it's only for t in my units a range of 20 in the span of t going from minus infinity to plus infinity. So just a few pointers on that. It's an elastic scattering process. So it's an elastic scattering process, but there will be some time delay. It's this time delay that we're after, as that is going to be related to the phase shift of the solution. Notice that the endpoints of this magnon remains fixed in the solution. So this endpoint I have at the top and one at the bottom, these are fixed all the time. The way you can think about this is that this is an operator due to a sea of z's and two impurities. And I will have a bunch of z's to the left of this, to the one impurity, a bunch of z's to the right of the second impurity, and those z's will always remain that location, and that's where they're sitting roughly. Then there's a bunch of z's sitting in between your two impurities that you have. And now what's happening here is that, well, the dilatation operator I should think of as the Hamiltonian. So in order for these two impurities to see each other, they need to be brought close to each other by time evolution. So in other words, I need to introduce enough loops in the dilatation operator in order to bring them, in order to deplete the z's that's in between them before they start coming together. When they start coming together, then this is the form that you see. And this only happens for a small period of time, and then you can think of them as two well-separated Magnon solutions again. Energy is conserved throughout. That's the other point. You can compute what's the energy of this configuration. It's a constant in time. And this cusp that you have, this moves in a straight line. Now what's interesting about this is that magnons in this coordinate system is represented by straight lines. So this tells me somehow that there is a frame I can choose, possibly in between these two excitations, where possibly moving along the center or something like this, but where the effective description is more closely related to not two separate magnons, but a single two-charge magnon with momentum P1 minus P2. That's what's represented by this straight line here. I'm still not entirely sure how to think about that, but this is at least a picture that you can generate for these straight solutions. Now, the statement that it moves along a straight line, as observed in these solutions, this is as a consequence. You can show that in an LLM geometry, this is the consequence that along that line, this is the equation in time that y should satisfy. So you can impose that the equations of motion are satisfied at the point. This is a very particular point because the number go to Lagrangian also vanishes at that point, so you need to treat it quite carefully, but after a careful treatment, this is what comes out. This xr appearing over there, that's exactly the x coordinate of this one that I have. I should point out that I use the freedom to rotate things so that it moves along a straight line. X is equal to some constant. But you can, of course, change the frame. But this is the equation that is satisfied.
So this grade is fine.
So, okay, so the solution I've plotted here is for ABS5 because S5. But if you study a general LLM geometry, then this is the equation that you must satisfy at that straight line. If you make the ansatz that there must be a straight line in the solution, then this is, well, a straight line where this cusp is appearing.
But for LLM, you have more general situations.
Yeah,
right?
for LLM, this is the solution that you get from that. If I plug in the choice for V5, it yields AS5 plus S5. You get a motion that you can solve analytically, and you can show that that is the correct time. Well, that's the correct equation governing this movement of the cusp along this line over here. So this is really useful because, and this is perhaps just one of the things that I wanted to add over here. I suspect that with this, one now has enough boundary conditions to satisfy or to solve this thing quite easily numerically. So the way to do that is to think of the solution not as two separate magnons, but think of them as two stringy solutions that are glued together at this cusp. So for example, I'll take the bottom magnon over here, it's starting out in this configuration, and now as I evolve in time, it goes from this larger magnon to this smaller magnon. And this, of course, energy is not conserved over here. In order to conserve energy, I need to glue this together with a smaller magnon becoming a bigger one. But the point is, I know exactly what this coordinate does as a function of time. And I know this happens at time is equal to minus infinity, time is equal to plus infinity. So I have a closed triangle for which I know exactly what the time on each of these lines should be. And that should be enough boundary conditions to satisfy the numerically, which is definitely something I want to try in future. For now, I'm still a little bit more ambitious. Perhaps it's a bit of a red herring, but this is getting to the thing that I really did want to show. And this is that what this is also telling me is that if I restrict the solution to this triangle over here, I'm only focusing on one part of the scattering solution, and the Sperton-Wolovich solution. And each point inside this triangle, except for this corner point I have over here, has a unique timeline. So, for example, this configuration and these ones never cross in time. There's no crossing point between these solutions. And this hints that you can write the Sperton-Wolovich in a form where time is really the component that you're after. And you can massage the solution a bit, and this is what you come up with. So here I've written down time as a function of x and y. This is an equivalent form of the Sperton-Wolovich solutions, where I've now written time as a function inside this triangle. And it's a reasonably nasty looking thing, but all of these arguments inside the logarithm are really geometric pieces of information. So one of them, for example, tells me that there's a line over here, another line running over there. The x's are restricted to lie between this x to the left and x to the right, and that's exactly these lines that you have over here. So even though the solution does look a little bit strange, it's basically just conveying a bunch of geometric information for the scattering process that you have over here. The one thing that I also want to point out is that, and I'm still not entirely clear how to think about this, but the center of mass velocity, that's key to determining the time delay of this process. It's also written entirely in terms of just geometric numbers that I have. So what's this line's x position and this line's x position? And that gives me a center of mass velocity. And this is also something that I found kind of curious. If that is the case, then one could make a geometric argument possibly for what the time delay for any scattering process, even the inelastic one, should be. If one could make that argument, that it's just a geometric quantity. Now, but as I said, this is the Sperton-Wolovich solution written in a very particular way.
What do you mean by inelastic?
Oh, that's if I have Magnon stretching between different edges. So, for example, I'll have a Magnon stretching from R1 to R3, and then a Magnon stretching from R3 to R3. You can, the argument for computing the kinematic part of the S matrix still works, so you can write that down. And in that you use energy conservation, momentum conservation, and charge conservation in these. So that you start out with two single magnons, you're going to end up with two single magnons. And
but is that situation integrable or
no?
that's why you can have
Precisely. So the scattering process here is going to be something that's going to be in the lab between these two magnons. But if you can argue that the center of mass velocity should just be something geometric, then this is a possible way to write down what the phase for that process should be as well. So now that I've found this form, I just want to perhaps reiterate that I think over here is already enough for a numerical solution. But if you're a little bit more ambitious, then you'd say that, well, this is suggestive of, let's just study the equations of motion where I try to solve for time in these equations of motion for a general LLM background. And what you do then is, well, I set x is equal to Walsh time and y is equal to sigma, which is a bit strange. But what do the equations of motion look like if I do this? So the only argument left is going to be time. You find that the equation of motion that you generate, well, there's three of them. There's an equation of motion for time, one for r, and one for phi. You can show that these three are proportional to one another. So I only need to focus on one. If I can set that equal to 0, then the other three are guaranteed. So I only get a single equation of motion. This equation of motion is nonlinear, however. Nonlinear and with second order derivatives. And what you can see also is that if I set time is equal to a constant, I satisfy them automatically. So the equations of motion only depend on the first and second derivatives with respect to time. So you could say, well, let's just do the following trick and let's just introduce these two variables that depend on the first derivative with respect to time, so u and v. So that simplifies the equation of motion a bit, because now I'm only going to get the equation in the first derivative of u and v. I also need to satisfy a consistency condition, however, because txy, the derivative with respect to y, then the derivative with respect to x of t should be the same as the derivative with respect to y and x of t. So I get an equation of motion and some consistency condition between u and v. But these are the two equations, still nonlinear. If you then do the following step and rather write the things in terms of these two vectors, so here I'm going to introduce u and v and minus v and u, then you find that you're still going to be nonlinear, but the nonlinearity is no longer going to sit along with the differentials. You've split these two. And now you just need to satisfy a condition that these two are orthogonal to one another and have the same norm. And you get the simplest equation of motion if I just rescale these vectors a bit. And this is just what I wanted to show. The equations of motion that you get when you do this look, in my mind, extremely compact and simple. So you get two things that tell me the divergence of a vector should be equal to some scalar number. They should be orthogonal, and here's just the relation relating their sizes. And what's furthermore is that this number you have on the right-hand side, this v derivative with respect to phi, is just the sum of different terms that I should have. So what I've been playing around with not a lot of success is writing down an ansatz for the solution and some combinations weighted with a function. So take two spread-and-Volovich solutions, different momenta, and then sit in front of them some arbitrary function r, and see if you can satisfy these four conditions over there. They've not worked, but as I said, I suspect that there should be some process with which to take a known solution of this with v phi and use that to generate solutions with a general v phi. I might be a bit too ambitious, but this is what I have. And as I said, these equations, at least to me, were quite surprising how compact they are. You get this very long non-linear partial differential equation, and it can really be reduced to this form over here. If you can find a v1 and v2 that satisfy these conditions, you can invert the process to eventually find what should the analytic form for time be for these scattering solutions for an arbitrary LLM geometry. This, as I said, this might be a red herring, might not be solvable, but this is I find it at least interesting. If this does not work, then we can always revert back to numerical analysis of these things. I should point out that what we're after is the time delay. So you want to compute the time delay for this process, so you'd have to figure out how to extract it from something of this form. But once you have that, you compute the phase shift, and it's this phase shift that you want to match with this conjecture, that it should just be a simple rescaling in the algorithm. That's essentially all I have to say on the scattering solutions. As I said, it's still very much a work in progress, but I'm confident that a solution is close. So what we want to do is compute this phase shift. That would provide a very explicit check of the conjecture. And you could possibly even study this inelastic scattering process in this as well, which I think would be really interesting. In the longer term, this should just be a check of this conjecture that these emergent gauge theories are isomorphic to Lessig form. And this, I don't think I mentioned this in the slide, but this is significant because we know planar Lessig form to be integrable. So this conjecture entails, among others, that the emergent gauge theory, the planar emergent gauge theory that each of these corners should also be an integrable theory, which is quite remarkable. It's integrable, and yet it's far away from this planar limit of the theory. In the sense that the background is certainly not a planar object, or describable by some planar diagrams. And that's a problem.
Questions?
One quick one. So, did I understand correctly that you mentioned three more with with large number non-planar limits?
Yeah.
And from that getting the planar limit?
So not quite. So keep in mind that the non-planar feature here is the background. Yeah? So this is an object that has all the n squared boxes. So if you were to compute correlation functions between an excited background and an excited background operator, you can't just sum the planar diagrams in this case. But if I take the collection of all excitations that I can attach to one of these corners, and I say this collection of excitations, I restrict these to only be of length or the square root length, then that is a basis for the planar limit of this emergent gauge, and that is where Mandelstam is. So it relates back to the question of Costa said. So you have to separate the background that's built up of a very large number of fields and the excitation that I'm adding. So for even the finite size effects, you still have a large in for the background that gives you this classical geometry, but I have finite in for the excitation that I'm attaching in a particular corner of this diagram. And attaching it to a particular corner, if you're studying these fields called primarily from Z's, fits very simply into a boundary condition form. A boundary condition for your excitations, and there are as many boundary conditions, valid boundary conditions, as there are corners of the jump diagram to get out.
No question, actually a bunch of questions. There's a sense in which the S matrix of the two magnons have a pole when you analytically continue momentum and you end up on the straight line. So this is one way to determine where the poles of the S matrix are, and then some other stuff gives you the have you thought about that way of thinking about it?
Correct me if I'm wrong, but so the poles that you get in the kinematic model of the S matrix, that's for two single charge becoming a two.
Yeah. So the point is that the S matrix is designed so you get a pole and the bound state.
Yes.
So the big question is, when you have two of these things and you're trying to scatter them, there should be something that encodes that. That's one way to get at this information. And that's the one that would be the long one connecting the two objects,
yes,
for example. But then the short one is kind of like doing an inversion of one of them. And then there's some statement from Yannick, what's his name? Yannick, yeah, that there's some sort of crossing symmetry. The question is this thing the crossing, is this line the crossing momentum to the other one in this thing or not? Do you know?
I don't know.
You know?
I don't know.
I don't recall the work of Yannick, but I've seen the crossing symmetry argument in the context of the S matrix that determines this overall phase.
Well, it's part of it. There's this. When they were trying to get there's this dressing factor to try to get it, they use some sort of crossing symmetry somewhere. So I was wondering if this is related to crossing symmetry or something. But,
that is certainly a strategy that one could employ to tackle the problem more, I think. I think one would have to look into it, but this crossing symmetry, if you have this very large number of Z fields making up the background, whether it's still valid in that case and so forth. But there's certainly a possible way to tackle it.
Okay, here's another one, which is when you're really going between two edges. Or when you try to, there's some sense in which you cannot form bound states any longer, and then the big question is what can one do about the S matrix there? I mean, there's a problem with things stretching between crossing from black to white. There's a problem with the solutions. How right? The white ones are in the SL2 sector, the piece of string that are in the SL2 sector, and then the other ones are in the SO6 sector. And you have to patch these two things together through, and then it kind of doesn't work in some sense, I think. So is there? Have you thought about that?
So I thought a little bit about that. So in the context of, so I must just say that it might just be, might just you be a bit naive in it, but at least these giant Magnon solutions you write down here, the classical string theory, these ones, if I compute the number go to action, the V phi dependence falls out completely. So in that sense, the classical Localized is not sensitive to V phi at all. But if I was to think of this as the dionic giant magnons, they certainly are sensitive to these poles. And
that's the one.
As a limit of, I send the number of Y charges to just be one or the one, then could be problematic. I'm not quite sure how to think about that yet.
Yeah, you have to work with the dionic magnons to actually
Yes.
figure this out. And I think that something's going to fall down.
Also something else you probably mentioned, but I got confused about it. This phase shift you're looking at, that's a gauge coupling dependent quantity.
Yes.
Right. So it's entangled on the gauge theory side, presumably, by some spin chain like scattering.
So,
and although these are not exactly the same spin chain because they're attached to this big operator.
yes, that's right. Yeah. So,
But is there a calculation of the gauge theory in this phase?
So you can certainly, if you go into high and high loop order, you start computing this quantity perturbatively. This string theory computation is trying to look at the strong coupling limit of that.
Yeah. So my question was, what are you actually trying to achieve? Are you trying to compare perturbative calculations on one side and maybe doing the string calculation and then doing some kind of one loop from the string side?
Oh, so
I'm trying to see if they match, if they go in the right direction, because
so
there's different quantities, right?
absolutely. So in this case, the thing we're trying to check is whether it's true that if I go to an LLM background and I just have these excitations attached to another corner, if it's just this rescaling of the coupling. And this is good because the exact dispersion equation for the ADS5 cross S5 ones are known, and these giant Magnon solutions, these Spadin-Volovich ones, you can compute the time delay and the phase shift from these explicitly and compare it to that strong coupling S matrix phase. In our case, we don't, we have a conjecture that the S matrix phase is just scaled, but in this case, all we need to check is that the answer we get for the phase shift, if that is just a rescaled version of the ones that Hoffman and Mandelstam have computed in their giant Magnon spectrum. If it is just a rescaled version, that's a confirmation of the conjecture, the strong coupling.
Any further questions? Okay, if not, let's thank Jaco again.